All right, so if you're working with data, you know the drill. Tables, rows, columns. It's your world. But what if I told you that hidden inside all that structured data is a powerful mathematical language that can unlock completely new ways of seeing things? Today, we're going to translate the world of databases into the language of linear algebra.
Look, I get it. You've got your SQL skills down, your data's all neat and tidy in tables, and everything just works. So why bother with a whole complex branch of math? Well, the reason is actually pretty simple. It lets you ask questions of your data that SQL can't really answer. Let me show you what I mean.
So how do we build that bridge? Well, it all starts by looking at a single row of data in a totally new way. We're going to take something you see 1,000 times a day, a regular old database row, and turn it into the fundamental building block of linear algebra.
Okay, so check this out. Here's a totally normal database row, a user ID, a salary, a tenure. Now let's do something really simple. We're going to ignore the user ID for a second because it's just an identifier, not a number we can really calculate with. Let's just strip away the column names and keep the numbers. What we're left with is this ordered list, 83,000, 8.7. And this simple little list, that's our way in.
And that little list of numbers? Well, in the world of linear algebra, that has a special name. We call it a vector. And that's really it. We've just turned a database row into a mathematical object. You can actually think of this vector like a set of coordinates, plotting our user as a single point in some kind of employee space, where the axes are salary and tenure. So we've slapped a new label on our data. Big deal, right? But the real magic isn't in the name. It's in what you can do with it now. The real power is in the new operations this form unlocks.
Yeah, and that's the million-dollar question, isn't it? What's the payoff for this little mental gymnastics routine? Well, once our data is in vector form, we can throw all sorts of powerful math at it directly.
Let's start with something super simple, addition. And the cool thing is, it works exactly how you'd think it would work. No tricks here. You just add the numbers in the same position from each list together, the first with the first, the second with the second, and so on. So you want to add vector v to vector w? Easy. We just take the first numbers, the 1 and the 2, and add them together. That gives us 3. Then we do the same for the second numbers, the 2 and the 1, which also gives us 3. And voila! Our new vector is simply 3, 3. It's really that straightforward.
And look, addition is just the tip of the iceberg. We can do subtraction just as easily. We can stretch or shrink vectors by multiplying them by a single number, and we can even get a little fancier with something called the dot product. And this is where things get really interesting, because these simple tools start to build on each other. That dot product thing I just mentioned, it helps us answer a question that seems kind of weird at first. How long is our data point? So in linear algebra, we don't just call it length. We get a bit formal and call it magnitude. And what it does is boil down that whole vector into just one single number that tells you its overall size or scale. For our user example, the magnitude would give us one number to represent their combined salary and tenure.
Okay, and this is where it all clicks. This is the big aha moment. When you can subtract two vectors and then find the magnitude of what's left, you've just figured out the distance between them. Now just stop and think about that for a second. We can now put an actual number on how similar two database rows are. How much alike are user A and user B? We can measure it. That is a total game changer.
All right, that's awesome for one row of data, but, what about the whole shebang? What about the entire table?
Exactly. A real-world database isn't just one row. We're talking thousands, maybe millions of them. We need a way to wrap our heads around that whole collection of vectors all at once. And the answer to that is something called a matrix. It's actually super simple. If a vector is just a list of numbers for one row, a matrix is just a list of those vectors. You just stack them all up. It's the perfect mathematical stand-in for an entire table of data.
And that's the key takeaway right there. A matrix is to vectors what a database table is to rows. Boom. We've just translated our entire table into this new mathematical language. But again, this isn't just a fancy new way to store numbers. Turning our data into a matrix unlocks some seriously powerful ways to see the hidden patterns and relationships inside the data.
Right, so what's the practical application here? What does this actually let us do? Let's look at a really solid example where thinking in matrices just blows thinking in rows and columns out of the water.
Okay, so what you're looking at here is called an adjacency matrix. It's a really clever way to represent a network, like friendships on a social media site.
So think of each row and each column as a different user. If the number where a row and column cross is a 1, it means they're friends. If it's a 0, they're not. So you can see right away user 0 is friends with user 1 and user 2.
But the real genius here is how fast this is. You want to know if user 0 and user 2 are friends? You don't have to run some complicated SQL query. You just look at the grid, row 0, column 2. It's a 1. Yep, they're friends. It's instant. You want to find all of a user's friends? Just read across their entire row. This is just a way more efficient way to handle this kind of network data.
And look, this is just one cool example. Representing networks is super powerful, but we're barely scratching the surface here. This stuff, linear algebra, it's the engine running under the hood for tons of data science techniques, from the recommendation systems you use every day to machine learning. So let's just do a quick recap of the journey we just took. We started with something we all know, a database row. We turned it into a vector. Then we scaled that up to a matrix to hold the whole table. And we even saw how that matrix can map out an entire network of relationships.
And that really brings us to the final, most important thought. Now that you can see your data in this new way, as vectors and matrices, as points and structures in space, what new relationships could you find in your own data? What hidden patterns are just waiting to be explored?
Because finding those hidden structures is what this is all about, right? So if this explainer helped you see your data in a new light, hey, we'd really appreciate it if you'd like, share, and subscribe. That way we can dig into more of these powerful ideas together. Thanks so much for tuning in.